Christopher's our first speaker up, so he's going to be talking about extending the preconditioning approach for low Mach, Navier-Stokes for multi-component flows. So I'm looking forward to it. So good to have you here again. You were here last year and enjoyed the talk, so take it away.
Okay, thank you so much for attending this presentation. Well, in this presentation, we are going to talk about how to extend the preconditioning approach for low Mach number Navier-Stokes equation for multi-component flows in SU2. No, how can I move this? Or should I use it? Okay, so currently the species transfer model is almost complete within SU2. We already have a validation and verification test case for a species transfer model in the main SU2 website, thanks to the work of Sam Bosman from TU Eindhoven. However, we still have a problem, which is regarding to the energy equation. When the specific heat capacity as a constant pressure depends on the mixture composition, the energy equation does not work correctly. As you can see here, we can obtain a physical result where two streams at the same temperature mixes. We have something like this, which is some physical, and I will explain this in some slides later. So we propose to extend the preconditioning approach for multi-component flows. So in order to do that, we start considering the energy equation for non-reacting flows in terms of the sensible enthalpy, which is given by this formula. This is the equation, and the sensible enthalpy is computed as the integral of the specific heat capacity at a constant pressure of the gas mixture with respect to temperature, and this specific heat capacity at a constant pressure of the gas mixture is computed as a mass fraction average of the individual heat capacity of the species I, where, by the way, Yi, the mass fraction of the species I, Bi, the diffusion velocity of the species I, and omega T is the heat release due to chemical reaction in this situation. So term 1 here in this formula represents the variation of pressure. Term 2 is the viscous heating. Term 3 consider the volumetric heat sources, and term 4 are the body forces on the species side. So if we consider the low Mach approximation, or also well known as the combustion approximation, this term vanishes. We can also assume that the viscous heating is negligible, and we are considered that there is no volumetric heat sources and no body forces. So if we do that, that equation reduces to equation 4. And now we can consider the sensible enthalpy of the species I, computed as the integral respect to the temperature of the individual specific heat capacity of the species I. So if we use this sensible enthalpy of the species I, we can write the sensible enthalpy as a mass fraction average of the individual sensible enthalpies. Then, if we use this definition, we can write equation 4 as an equation for temperature, and after some mathematical manipulation, we reach this formula, where here we have the terms related to temperature, we have a term related to the heat release due to chemical reaction, which is defined like that way, and we have a term related to diffusion phenomenon. For now, we are going to consider that non-chemical reactions are involved and that the diffusion effects are not important. Then, if we do that, we obtain the following energy equation for non-reacting flows in terms of temperature. Currently, in SU2, we solve this energy equation for incompressible flows. However, we would like to solve equation 8 instead of equation 9 for multi-component flows. So in order to do that, we are going to divide that equation by the heat capacity, and using derivative rules, we obtain the following energy equation, which is given in this form. So this equation is the one that we are going to use in the preconditioning approach. From this point, we are going to follow the derivation made in the original work done by Tom Economan, where first we write the Navier-Stokes equations in conservative form given by equation 11. The conservative variables now are given by density, density times the velocity, and density times the temperature, instead of the original working variables where Cp was involved here. Also, the convective, viscous, and source terms are given here. In red color, you can see the main difference. In the convective term, Cp is not longer there. In the viscous term, we divide by Cp, and here there is a new source term. Then, equation 1, equation 11, we transform this equation 11 from conservative to non-conservative form given by equation 13, where the working variables are pressure, velocity, and temperature, and m is the Jacobian of the conservative variable with respect to the working variables. Where this matrix, we highlight that the last row, which is the one that is related to the energy equation, now is independent of the heat capacity. Also, rho p is the partial derivative of the density with respect to pressure, wherefore in compressible flow, we assume that this is 0, but for the preconditioning, we are going to replace this one by a preconditioning parameter. And this one is the partial derivative of the density with respect to temperature. Then, if we multiply equation 13 by the matrix K given by this way, by this expression, we obtain equation 15, and we can analyze the product of matrix K times M. And if we compute this product, we reach this matrix, and this matrix allows us to define our preconditioning matrix given by this expression, where the partial derivative of the density with respect to pressure is this parameter, which is called the preconditioning parameter, which is the same choice made by Tom Economan in his original book. So we multiply equation 15 by the inverse matrix of K, and we obtain the final implementation given by this formula, and the matrix tau is given by this expression, where again we highlight that this last row is independent of Cp. So in order to test this extension, we are going to consider an existing test case in SU2, which is thanks to Tobias Katzmann, which is a 2D compressible mixing channel where we have two streams. Here we have a stream of pure methane. We have two different heat capacity, one for methane and one for air. The temperature here is 300 Kelvin, and the velocity here is 0.1 meter per second. At the inlet too, we have a mixture of air and methane, the same heat capacities, and the same temperature and velocity. We also consider a symmetry plane here, non-adiabatic, non-slip adiabatic wall in green, and at the outlet we consider zero pressure as a boundary condition. Then our first simulation is two streams with equal temperature. As already said that we are not considering any volumetric heat sources, no chemical reactions are involved, we expect that the solution here, respect to the energy equation, will be a temperature of 300 Kelvin everywhere. So if we compare developed with this new extension, we obtain the following result. As you can see here, we develop, we obtain creation of a cold layer here and a hot layer here when the stream mix in this area, which is completely unphysical. But if we use the extension, we obtain the expected result, which is a temperature of 300 Kelvin everywhere in the everywhere. Now we are going to test the following case where we have two streams with two different temperatures. We have a hot stream here with 350 Kelvin and a cold stream here with 300 kelvins. So under the same conditions, we compare developed with this extension, and we obtain the following. In developed, we obtain this solution, which is again a physical, because here we see a hot stream, then we see a decrease of the temperature here, and then an increase here, which is physical because we are not considering any volumetric heat sources and no chemical reactions are involved there. But with the extension, we obtain a physical solution where we can observe energy transfer from the hot stream to the cold stream, as we expected. Now this extension provides more robust simulation, because if we switch the temperatures, if this one now is the hot stream and this one now is the cold stream, and under the same conditions, we compare develop and this extension, and we observe the following. We develop now, we obtain a more physical solution, but however, the solution obtained using develop is unbounded, because here we can see that here the temperature goes over 350 Kelvin, and he goes below 300 Kelvins, as you can see here in the bar. However, if we observe the result with the extension, we still obtain a physical result where there is an energy transfer from the hot stream to the cool stream, to the cold stream. Finally, this simulation provides better numerical results, because if we compare the residuals of the temperature using develop and the extension, we observe that using the extension, we reach precision maximum after some iterations, but if we use develop, at some point, the residual become flat, which is not good for the discrete adjoint design, because for getting good results using the discrete adjoint design, it's well known that we need a very well converged solution. So we can conclude that the preconditioning for multi-component flow is extended to account for variable heat capacities. The implementation is in SU2, is verified and validated. And we expect to create a pull request in SU2, plus adding the diffusivity term that we rejected in this presentation. And the next step is to couple Cantera to SU2 and implement detailed chemistry for incompressible flows. So next conference, we expect to show you how to simulate reacting flows in SU2, and probably how to use the discrete adjoint solver for reacting flows. Thank you so much for your attention. Is there any question?
Okay, thanks, Cristopher, for a great talk. So we have one question up front. This is the root cause of the issue.
Here?
Yeah. So you mentioned that the issue is that we have CP outside and
Yes.
CP inside.
Yes.
Why don't we put CP inside?
Because now CP depends on the Mitchell composition. So it changes along the field. It's not longer zero the gradient of CP.
No, yes. Why isn't the solution just putting CP inside of the
And why not put this? Why not put this inside?
Yeah.
Because if we put CP inside, we should type this in a different way, because CP can also change on time, and also can change because in this part. Because if we use derivative rules, this one, if we split, if we compute the gradient of this, we will reach CP, the gradient of raw temperature, velocity, plus raw temperature velocity, dot product, and the gradient of CP. And the gradient of CP is not longer 0. So we at the first we tried to do that, and that didn't produce any result in the original implementation. That is why we decided to extend the preconditioning in that way.
So you had another like convective term that was CP times
Yes.
or gradient of CP times
Yes.
something.
Yes.
The product.
Yes, yes, yes. Here now the convective term is this one. By the way, if we use the same approach, at some point we reach the same preconditioning convective matrix. And if we compute the eigenvalue remain the same. So all the procedures that you made keep the same, the whole structure. We only need to change this matrix and the inverse of that matrix.
What I'm thinking is that there's two steps in the precondition. One is the converting the equations from
Yes.
conservative,
Yes.
and then there's
Yes.
this kind of sounds like the conversion from conservative to primitive variables is breaking some assumptions because of the variables.
Could be. What is it? K? I don't remember which one is the conservative.
So there could be a way that you can get the same result without using the extra source. Like, we can all
Yeah,
Okay.
that's great. Maybe time for one more question.
Yes, thank you. So, at the end, you mentioned that you want to include this fuse effect.
Yes.
Earlier you mentioned that the fuse effects are not important.
Because I wanted to highlight for this presentation that we must solve that equation instead of that one. That is why I did not include the diffusion term. If I include the diffusion term, the simulation will only improve. Because before doing this, we included the diffusion term, and the diffusion term didn't have any effect in the result. It's like the preconditioning was more strong than the diffusivity terms. That is why we didn't consider in this point the diffusivity term.
Yeah, they're not impacted by the
Yes,
preconditioning.
yes, that is why.
Any other questions? Yeah, Mark.
Yes, thank you for the call. I have a question. So maybe you said it, maybe I missed it. All of this is being implemented in the incompressible software.
Yes, in the incompressible software. Yes.
And then the result is my total ignorance about it. So everything meaning maximum going to an energy ratio transform in a couple fashion, or I'm not sure.
Yes.
It's all counts there. The second question is, what is the range of temperatures that you expect to be able to deal with this implementation and further inclusion of MTR? Is the maximum temperature?
The maximum temperature.
Yeah, the type of problems that you're dealing with, right? So can reach what is the temperature that you can reach at most, and you still deal with this work. Just to give some boundaries.
To be honest, I don't know. I'm not sure what is the maximum value. 2000?
2000 Kelvin. Okay.
Thank you.
And let's thank the speaker, Christopher, once again.